Thank you. So yes, my name is Matthias Blum. I'm working in the InterPro and PFAM team at MBBL, and yeah, today I will be excited to talk about how we improved the InterPro resource using AI, and more specifically large language model and deep learning. If you don't know what InterPro is, you might be in the wrong room, but since we're not many, please stay, and I will...
Sorry about that sound online. Excuse me.
Oh, it's all right.
It's fine. Transcription works. Okay, I don't know.
Should I resume?
The subtitle will work.
Okay. Sorry. So yeah, sorry about that. So InterPro is a resource that functionally analyzes protein sequences and classify them into protein families, but also detect the presence of domains and functionally important sites. And it does this by integrating predictive models and that we call signatures from different databases, member databases such as PFAM, Prosite, Panther, etc., etc., etc. Some of the, if you have seen my talk from yesterday on InterPro, you might see some of these slides a bit repetitive, so sorry about that. I hate single-use slides. So an InterPro is the software that scans sequences against those collection of predictive models to characterize novel sequences. And on top of that, InterPro curators integrate the signatures into InterPro entries to remove redundancies, but they also add functional annotations and Go terms and literature reference, and etc. So this is what an InterPro entry looks like on the InterPro website. So this one represents the C2 domains. It has a name on top, and then you have a short name, which is kind of an easy to remember identifier. On the right, you can see it has 4 contributing signatures. This entry was created to form 4 predictive models of 4 different member databases. Then it has a description that talks about the function of the domains, and on the bottom it has reference to the literature. Most of the time, those descriptions are not written from scratch by curators. They are derived by description provided by the different member database, but that's not always the case. So in this graph, you have the number of signatures provided by individual member database. In green, you have the signatures that come with a description, so it's easy to integrate. And in red, you have the bad ones that comes without a description. That means more work for curators because they have to go through the literature. So it's a labor-intensive work, and that means, of course, that slows down the integration rate of those signatures. So we thought, how can increase the rate of integration? How can I help curators do this difficult job? So we turn out to large language models. So for this, we use Swissprot entries because it's a reviewed section of UniProt KB. It has high quality manually curated annotations. So what we did is for each protein family, we collected the matching in Swissprot entries, and we extracted key information from those entries, such as the name, the comments about function, etc., etc. This slide is a bit outdated because at first large language models had a context window a bit small, so you couldn't feed it a lot of information. You had to be very selective of what you would give. But nowadays, with large commercial models such GPT-4, GPT-04, or the context window size is huge, so you can just stuff the UniProt KB flat file, and then because it's a well-structured file format, it is also well understood by the large language model. It's the model is able to understand that. And on top of this, we had instructions such as using the data provided, please generate, or no, please just generate a summary of the description of the protein family. Of course, InterPro entries, as I mentioned before, just don't have description. They also have a name and a short name, so we change our pipeline. So in the end, the large language model would generate a JSON that contains all the information we will need to create an InterPro entry from scratch, because that was our goal. Have a one push button that takes a protein family, and all the way we can generate InterPro entry without human intervention. So that's what we did. We were able to generate annotations for over 5,000 protein families with LLMs. And out of these 5,000 protein families, we were able to create 4,000 new InterPro families, new InterPro entries that represent a protein family, again, without human intervention. So that shows, this graph shows the the growth of the number of InterPro families in the database over years since 2000 until 2004. And in green, you have the one created by curators, by expert curators. And in red, you have the one created by AI. And that's quite a big jump. And with the current pace of curation, it will have taken roughly 5 years to reach this. Of course, we don't expect LLM to replace curators, and we don't just regenerate these InterPro entries using LLM for them to gather dust. What we want is basically have a kind of a system that creates boilerplates InterPro entries that curators can enrich. So on the left, you have a description that was generated automatically using LLM. It was unreviewed. And a couple of weeks later, a curator came and made some slight modification to the text and then added a literature reference. This is a nice way to increase the pace at which we create entries in the database. Something we try to do is use a local model. So we wouldn't have to pay for commercial model because, saving money is nice. So what we did is we took a local a model that was already fine-tuned on scientific text, and we further we call it the baseline, and we further fine-tune it with using GPT for description. So description that were generated by a commercial model in the way to kind of the local model to mimic the quality of those descriptions generated by the commercial model. And what we did is we took those descriptions generated either by the commercial model, by the baseline model, by the fine-tuned model, and we put them in a pair of those descriptions in front of curators of the same protein family without telling them which description came from which model and say, choose the best one. And the commercial model was slightly preferred of the fine-tune, but that means the fine-tune is a viable option if we really want to re-annotate a large scale of protein families. Of course, sometimes, and more than often you would like, protein families don't match any Swiss prot sequence. So what do you do in this case? Well, what we try to do is using gene instead. So we collected the gene that encode the protein matched by a protein family, and we search for open access, the open access literature. So we extracted snippets or sentences that contain those genes. And then for each gene that had several snippets or sentences, we use LLM to summarize, to create a kind of a unique description of this gene. And then for each gene summary, we use, again, LLM to generate a description for that protein family. So the advantage is that you don't need Swiss prot data, you don't need Swiss prot annotation. And also because the description comes from the literature, you can actually have citation in your description to support your content. But that's also more complex. So again, we did this kind of pair comparison with curators. So we took protein families that already had a description written by a human expert, and then we regenerated the description using the Swiss prot approach that I mentioned before and the gene-based approach that I just mentioned. And again, not telling them what was the source of that description, we put them in front of them and say, choose the best. And interesting, the favorite description were usually the one generated using the Swiss prot approach, so AI generated, followed by the gene-based approach, AI generated, and the least preferred one were the one generated by human experts. So that shows that LLM are not just like a nice toy we can use. It's really a robust system that we can use in production to describe protein families and to update protein families in an automatic manner. So far I've discussed how we can use LLM to update or describe protein families, but what about finding those protein families in the first place, especially when standard traditional methods fail, such as HMM? And this is where deep learning comes or turns in. So since 2021, we've been collaborating with a team of Lucy Colwell at Google DeepMind, and her team has been developing deep learning model to predict at first PFAM annotation. So it was a deep learning model that was trained on all PFAM annotation, and that model was very, very good at not just replicating PFAM annotation, but also finding domains that PFAM HMMs were failing to annotate or to find. Eventually, the third version was trained on all InterPro data, so all the data come from PFAM, CDD, Panther, etc., etc. And earlier this year, we released it as part of InterPro 1.5, and it's this deep learning model and the prediction are called InterPro N. And this is a collection of 1.87 billion predictions across all uniprots. So these are available on the website. They are available on the REST API, and you can download them from the EBI FTP. So this is an example of a protein. And of course, you have the PLED score from AlphaFold on top. And then you have all the InterPro, the annotation that come from InterPro. But sometimes you have annotation that is not found by InterPro, but found by InterPro N. And in this case, you have it. So in this case, you can see on the right, the one that had the little sparkle icon are the one found by InterPro N. And this is a bit like, I mean, when you look at the coverage or the evolution, or in this case, more the non-evolution of the sequence coverage in InterPro, it feels a bit like the myth of Sisyphus. It doesn't really matter how many signatures you add to the collection, because you always have new sequences. So you can always stuck at this 84% of coverage of Uniprot, which is not too bad, but you will hope that after some time it will increase, or it will break the 85% bar. And over the past 5 years, we're stuck at 84%. And then suddenly you have this deep learning model that just boom, add your almost 6%. So that's very exciting. We're also thinking, can this deep learning model generalize? Because that's a good thing to have a new annotation for PFAM, but not all metadatabases in InterPro use HMM, and some they use HMM, but they have a different post-processing. So can we constantly see new annotation, more annotation across all the metadatabases in InterPro? And yes, that's the case. Even for very, very small database, very specific database like SFLD, that doesn't provide a lot of annotation in the traditional method because it's very specific. InterPro N provides or detects, predicts more annotations. And if you look at some key species of model organism, it's the same. So in dark blue, you have the coverage of InterPro using the traditional methods, and in orange, the coverage you can only achieve by using the InterPro N deep learning model. So those annotation or prediction are available in the website, download FTP and REST API, but they are not yet available in InterPro Scan, which is a software that is used to characterize sequences. But we're developing InterPro Scan 6. Too bad if you missed my talk yesterday. And InterPro Scan 6 is developed in Nextflow, and we can actually integrate deep learning models into this new pipeline, and InterPro N will be eventually added there. So you will be able to characterize your novel sequence with it. So far I've talked about predicting annotation, predicting annotation using sequence-based method. But would it be nice if we could use, if we could define domain using structures? Oh wait, we have AlphaFold. Oh wait, we have TED. So yeah, if you have missed the talk from Nicola earlier, so TED is this great method that use different domain boundary detection on top of the AlphaFold predicted structures to define consensus domains. And we're very excited to integrate all those TED domains in InterPro. So it's not too small. So what you have, again, it's an example of a protein. You have the PLED score, so the per residue confidence score from AlphaFold, and just below you have the TED domains, so predicted from the AlphaFold prediction using by TED, and then lower below that, sorry, you have a mix of InterPro domains, so the one that were detected in a traditional manner using HMM, etc., but also the InterPro N prediction that were detected using the InterPro N deep learning model. So that's really nice because it adds a new layer. Now we don't just have sequence-based domains in InterPro. We have also structure-derived domains. So that's very exciting. And on the right, you have the sequence coverage. I love sequence coverage graphs of InterPro N, and TED. So in light blue, you have the number of sequences that are found by multiple methods. And in dark blue, you have the exclusive sequence, so the sequence are only found by one single method. Maybe TED annotates fewer sequences, but it's also the method that has the highest number of exclusive sequences. So it's very exciting for creators because then they can use TED to create new PFAM entries or the database to create new signatures. And TED, thanks to AlphaFold, give us really a good insight on eukaryotic and prokaryotic sequence structures. But what about virus? Well, where the number of resolved structure and predicted structure from AlphaFold is very, very scarce. Well, thanks to BFVD, things are getting better. So BFVD is this big fantastic virus database. It's a database of predicted structure for viral sequences. So they took about 3 million sequence from UniProt, and they cluster it using sequence similarity. And then for each cluster, they selected one representative sequence, and they predicted a structure using Colabful. So those representative structures are obviously available on the BFED website, but we also integrated them into the InterPro website. So that's one last example. You can see the predicted structure from BFED. It looks like AlphaFold because it has the same PLET color scheme, but it's from BFED. And on the right, you have the normal domain viewer that you have on all protein pages in InterPro. On top, you don't have the AlphaFold PLET, but that's a PLET coming from BFED. And then after, again, you have the InterPro domain and the InterPro N domains. Maybe it was too fast. I hope not. So in summary, InterPro is not just growing in size anymore. It's really evolving. Now we have LLM that allow us to describe, create InterPro entries at an unprecedented pace. We also have new deep learning methods that either allow us to annotate more sequence than could ever before. And now we have this new layer of structure, pretty structure-based information from AlphaFold, of course, but mostly TED and BFED. And yeah, finally, you're just patting yourself on the back that we have a new version of InterPro 6. If you use it in your research, please test it. And with that, I would like to thank the InterPro team, especially curators, for accepting to be our guinea pigs when working on LLM, the team of Lucy Colwell at DeepMind, and Jan at UCL, who helped us integrating TED domains in the website. And with this, I would like to thank you for your attention.
Questions? I might be in the wrong room. What did you do pro again?
Out.
I was curious about the annotations with the LLMs, especially when you find that humans' pages, that humans' annotations are worse, or in terms of descriptions. But why so? It's like because it's like spelled in a natural way. Or?
You should ask curators, and some of them are behind you. I think most of the time is that each curator, especially when they're not native in English, they may have a specific way to write that means maybe not so, not fluent, but not smooth and nice, while LLMs, especially when writing in English, they know how to butter you up.
And last question was, so you mentioned that you have more annotations in InterPro than TED.
Yes.
Where are you getting these extra sequences?
Sorry?
I was wondering how you're getting these extra sequences, or if you're actually
So one of the reasons that we have fewer, one of the reasons we lose annotation in TED, it's because the AlphaFold database is kind of shrinking in size. As UniProt has new releases, they change, a sequence sometimes is removed from UniProt, or one amino acid is changed, so a sequence is updated. And of course, that means if you were predicting a new structure using the same sequence, it would be almost similar, but because there's even one amino acid, we just prune it. And that obviously is going to shrink slowly the AlphaFold database, therefore TED, the TED annotation in InterPro.
Thank you, very nice. I have a related question. So did you try taking the human curator annotations and just having them rewritten with the same information by an LLM, like rewrite this nicely for me and then compare? Because as you said, it's very smoothly written. And I think that would be a fair comparison. Because right now, I'm comparing more on the form aspect than on the content of the written mistake. So
we haven't tried that. Something we want to do in the future is to consistently rewrite all past description, but we could fine-tune the language model that's going to do this using the human written description. That's true. But yes, that's fair. We haven't rewritten the human description before doing this comparison.
One final question. Great talk, Matthias.
I just wanted to ask about
I
when
think the back isn't working. Can you check the switch? Should be on the right side. Should be moved from left to right. Yeah, I think it's working.
so when your the LLM is summarizing from the Swiss entries, I just wanted to see, is there a threshold, like the number of how many Swiss entries it can summarize it? Does it go beyond, like, loses the context, for example?
So if you have less than 3 Swiss prots, it's going to be, usually the description is going to be overly generic. So that's not going to make its way to InterPro. If you have too many Swiss prots, well, you're going to break the context. But in this case, it's very simple. You just do a random selection. Because very often a protein family, unless, I mean, I'm not talking about super families, I'm really talking about protein families of decent size. Usually they're going to match up to a few hundreds of let's say, different Swiss prots. If it matched 2,000, there's a very high chance that a lot of those Swiss prots are going to be exactly the same name and the same descriptions.
Okay, so we'll thank Matthias once again.